morning students, I welcome you all in this lecture of the numerical methods. In my previous lecture I was talking about the Newton Raphson method for finding a root of an equation. Now in this lecture I will solve question based on this Newton Raphson method. Then I will discuss about the order of convergence and rate of convergence, and then I will try to find out the rate of convergence of the bisection method. So let us start with the question of this Newton Raphson method. So perform four iteration of Newton Raphson method to find the smallest positive root of the equation fx equal to x cube minus 5x plus 1 equal to 0. So solution. Okay, here we have to perform four iterations of Newton Raphson method to find the smallest positive root of this equation. Now let us put x equal to 0 here. Then you can see that at x equal to 0 we have the value of the function as 1. At x equal to 1 this will be a 1 minus 5 plus 1. So this will be a 2 minus 5. So 2 minus 5, that means we will have minus 3. So it is positive and again it is negative. So it is clear that our root is between 0 and 1. So this implies that root lies in the interval 0,1. Now we have to guess the initial approximation, that means x0. Now as you can see that our root is near to 0 because at 0 the value of the function is smaller than the value of the function at x equal to 1. At x equal to 1 we have the numerical value of the function as 3. At x equal to 0 we have the numerical value of the function as 1, and 1 is near to 0. So we can assume x0 as 0.3, 0.4. But if you have any confusion, then take the initial approximation as the midpoint of the interval. So let us assume the x0 as 0.5. So here I am assuming x0 as the midpoint of the interval, but we can also assume x0 as 0.4, 0.3 and so on. Now our Newton Raphson method is now xn plus 1 is equal to xn minus f of xn divided by f dash xn. So this will give you xn plus 1 equal to xn. Now f of xn will be xn cube minus 5xn plus 1 divided by its derivative. So this will be 3xn square minus 5. So on cross multiplication this will give you 3xn cube minus xn cube. So we have 2xn cube. Then you will have minus 5xn plus 5xn. So this will be your 0. So plus 1 divided by 3xn square minus 5. So this is your xn plus 1. Now if you put n equal to 0, then from here we can see that our x1 is equal to 2x0 cube plus 1 divided by 3x1 square plus minus 5. So from here we will have the value of x1, and your x2 put n equal to 2. If you put n equal to 1, then your x will be your x2, and here in the right hand side we will have 2x1 cube plus 1 divided by 3x1 square minus 5. Now let us compute the values of x1 and x2. Now in the numerator we have so this is equal to x cube plus 1 3x square minus 5. So now at x equal to 0.5, our x1 is equal to, so this is your 3, here we have minus 1, this is your minus 1. So here we have the sign minus 1, this is your minus 1 and it is minus 1. So it is equal to 2x cube minus 1. Now the value at x equal to 0.5 is equal to 0.17647. Now the value of x2 at this x1 is equal to, now this is equal to 0.201568. Now the value of x3 at this x2 will be now this is equal to 0.201568. At this value our x3 is equal to 0.201639 and our x4 is equal to 2x3 cube minus 1 upon 3x3 square minus 5. So this is your x4, and at this value 0.201639 we have this x4 at 0.201639. So now you can see that our x4 and x3 are similar to each other. So that means we can say that our root is correct up to decimal 6 or 7 places. Therefore, as we have to perform 4 iterations, so therefore our x is equal to 0.2016396. So this is the solution of, this is the one root of this particular equation. Now let us derive an iteration formula for the equation derive an iteration formula for p root n and hence calculate the value of 17 power 1 by 3 and 10 power 1 by 2. Solution. Here we have to derive an iteration formula for pth root of n, and with the help of this iteration formula we will have to calculate the cube root of 17 and square root of 10. So solution, let us assume x equal to fp root of n, then your x for p will be equal to n. So let us assume xp equal to xp power minus n. So from here our f dash x will be p xp power minus 1. So with the help of the Newton Raphson method, by Newton Raphson formula, we have xn plus 1 equal to xn minus f of xn divided by f dash xn. So this is equal to xn. Now your f of xn is equal to xn power p minus n divided by f dash xn, which is your p x power p minus 1. Now on cross multiplication, this will become your p into xn power p minus 1. So we have p minus 1 into xn power p. Now this minus minus will become plus n divided by p xn power p minus 1. So this is your xn plus 1. So we have the value of xn plus 1. Now we can put n equal to 0, 1, 2, 3, 4 and so on to get the values of the remaining iteration. Now in first case we have to evaluate the cube root of this 17. So that means we will put our p equal to 3 and n equal to 17. And with the help of this iteration formula, we can have the cube root of 17. Now for the square root or for the cube root, this formula become for 3 root n, we have xn plus 1 equal to, now for a cube root of a number n, we will have xn plus 1 equal to, now this will become your 2 xn power p plus n divided by p is your 3, so we will have 3 xn square. So this is an iteration formula for cube root of n. For the square root of n, we have xn plus 1 equal to, now put our p equals 2, so this will be your xn square plus n divided by 2 xn, as our p is 2. So for square root of a number n, we have this iteration formula. Now let us calculate the cube root of 17. For cube root of 17, we will use this iteration formula. So our xn plus 1 equal to, our p is 3 and our capital N is 17, so this will be 2, your p is 3, so we will have 2 xn cube plus 17 divided by 3 xn square. So this is the iteration formula. Now we need the initial value of this cube root of 17. Now just guess the initial value of this cube root of 17. So we can assume this as we know that the cube root of 2 is 8 and cube root, okay, we know that cube root of 27 is 3 and cube root of 8 is 2. So that means this value is between 2 and 3. So let us assume x naught as 2.5. Then your x1 will be equal to, here we need the help of calculator. Now your x1, for your x1 we will have x naught as 2.5. So this is equal to x naught whole square plus this is your iteration formula. So just put n equal to 0. So this will be 2x naught cube plus 17 divided by 3x naught square. So this is equal to 2x square plus 17 divided by 3x square. In the numerator we will have x cube so we have 2x cube plus 17 divided by 3x square. Now if you put x naught as 2.5, then this is equal to 2.5733, and your x2 will be equal to 2x1 cube plus 17 divided by 3x1 square, and this is equal to 2.57, and this is equal to 2.571283. Your x3 will be equal to this is equal to 2.571281. Your x4 will be is equal to 2.571281. So therefore your x, that means your x means the cube root of n. Your x means the cube root of is equal to 2.571281. So this is our x. This is our value of x. Okay. Now let us guess the square root of 10. For the square root of 10, now for the square root of 10, you can also assume it. You can also take this polynomial like this x square minus 10 equal to 0. And for x naught, just put x equal to 1. Then you can see that this is negative. Put x equal to 2. Again, you can see that this is your negative. At x equal to 3, you can see that this is your positive. Again, this is your negative. So at x equal to 3, this is your 9 minus 10. So we have negative. At x equal to 4, this is your 16 minus 10. So this is your plus 6, which is positive. Now you can see that the square root of 10 lies between 3 and 4. So let our x naught is equal to 3.2. I am assuming 3.2 because at x equal to 3, the value is near to 0. At x equal to 3, we have the value of the function as minus 1. At x equal to 4, we have the value of the function 6, which is far than this minus 1. So let us assume x naught equal to 3.2. Now our iteration formula for square root of n is this formula. So therefore, our xn plus 1 is equal to xn square plus 10 divided by 3 divided by 2xn. So this is our iteration formula. Now with the help of this iteration formula, we can have the value of this square root of 10. Again, let us solve this square root. So in the numerator we have xn square plus 10, then this is divided by 2 times xn. Now if you solve this for this x naught, then your x1 will be equal to, your x naught is 3.2, so this is equal to 3.1625. Again put the value of x1 here, then your x2 will be equal to 3.1625. So this is equal to 3.16227. Again put the value of x2 here, then your x3 will be equal to, your x3 is equal to 3.16227. Our x3 is equal to 3.16227. So therefore we can say that our x is equal to 3.16227. So the square root of 10 is equal to 3.16227. And with the help of this Newton Raphson method, we can verify this answer. So this is the square root of 10. Here we have obtained the cube root of 27, cube root of 17. Similarly, we can obtain the reciprocal of a number. Now let us write an iteration formula for the reciprocal of a number. So our next question is, derive an iteration formula for reciprocal of a number n and hence obtain the value of 1 upon 11. So solution, let us assume x equal to 1 by n. Then this is equal to, we can also write it as n equal to 1 upon x. So your fx will be equal to 1 upon x minus n. So it is equal to 0. Now this is your equation. Here I am interchanging x and n, otherwise our f dash x will become, if you not interchange this x and n, then our fx will be x minus 1 by n, and we will get the value of f dash x as well. In that case, our xn plus 1 will be the same as xn. So here, that is why I am interchanging the x and n. So now fx will be this one. So your f dash x will be minus 1 upon x square. So therefore your xn plus 1 is equal to xn minus f of xn divided by f dash xn. So this is equal to xn minus f of xn, which is your 1 upon xn minus n divided by f dash xn, which is your 1 upon xn square. So it is equal to so therefore your xn plus 1 is equal to xn minus, now this minus minus will become plus, and this xn square will go in the numerator, so we have xn square. So your xn plus 1 is equal to xn. Again here we will have one more action, so this is your 2 times xn plus minus n xn square. So this is the iterative formula for reciprocal of a number. Now as we have to obtain the reciprocal of 11, so in our case the value of n is 11. So therefore your xn plus 1 is equal to 2 times xn minus 11 xn square. So your x1, now the reciprocal of 1 by 11 can be your 0.1. So we can assume the value for x0 as 0.1. So let us assume x0 as 0.1, or just put the value of n equal to 11 here. So if you put n equal to 11, then you can guess the sign of this fx, where this fx is positive and where it is negative, and with the help of that we can have the value of x0. Now your x1 is equal to 2 times x0 minus 11 times this x0 square. So this is equal to 2 times of this x minus 11 x square. Now this is equal to, at this 0.1, this is equal to 0.09. Your x2 will be equal to 2 times x1 minus 11 x1 square, and this is equal to, at this 0.9 we have 0.0909, and your x3 will be equal to 2x2 minus 11 x2 square, and it is equal to 0.0909. At this value we have 0.090909. So you can see that your x is equal to 0.9090. So this is the reciprocal of 1 by 11, and this is your x equal to 0.909. Now I will discuss the rate of convergence and order of convergence, and then I will try to find out the rate of convergence of bisection method, Raphson method, Iterative method, and Newton Raphson method. So rate of convergence. Okay, let xn be the sequence which converges to a number x, and let yn be another sequence of numbers which converges 0, which converges to 0, and there exists a number, say lambda, independent of n, such that modulus of xn minus x less than equal to lambda times this yn, then we say that the sequence xn converges to this number x with the rate of convergence order of y. Then we say that the sequence xn converges to x with rate of convergence O of yn. This capital O of yn is read as big O yn. Now what is its meaning? Here O of yn read as big O of yn. Now this big O of yn gives the reference how quickly this xn converges to this x. That means this O of yn gives you an idea which tell you how quickly this xn is going to convert this small x. Now suppose that here as n tends to infinity your xn is converging to this x. Also this equation can be written as xn equal to x plus O of big O of this yn. We can also write this xn equal to x plus big O of yn. Now here your xn will converge to x and your yn will tends to 0 as your n tends to infinity. Now how quickly your yn is going to tend towards the 0 will give you the measure which is known as rate of convergence. So the quickness of this yn tending to 0 is the rate of convergence. Here O of yn provides a reference for how quickly error approaches to 0. Consider let your an is equal to this sequence n plus 3 upon n plus 7. Suppose that consider the sequence an and bn where your an is equal to n plus 3 upon n plus 7 and your bn is equal to 2 power n plus 3 upon 2 power n plus 7. Now in the first sequence we have n, whereas in the second sequence in place of n we have 2 power n. Now as n tends to infinity, you can see that if you take this n common, then this will be your 1 plus 3 upon n, and here we will have 1 plus 7 upon n. So you can see that this sequence an tends to 1 as n tends to infinity. So that means we can say that this sequence an converges to 1. Similarly, if you take this 2 power n common, then this will be 1 plus 3 upon 2 power n, and this will be 1 plus 7 upon 2 power n. Again we can say that this bn converges to 1. So here both the sequence converging to 1. Here your modulus of an minus 1 is equal to this an minus 1 will give you, now this will be your, in the numerator we will get 4, so minus modulus of minus 4 will be your 4, so we can write it 4 into 1 upon n plus 3 less than 4 into 1 upon n. We can also write it as, because this 1 upon n plus 3 will be less than 1 upon n. Now Therefore, we can say that this an minus 1 is less than, now if you take this 4 as lambda, say this 1 by n is yn, so here we can say that this implies that, just see this definition. With the help of this definition, we can say that our an is converging to 1 with order of convergence of yn. Your yn is 1 by n. This implies that your an is converging to 1 with the rate of convergence, of 1 by n. So with the rate of convergence of 1 by n, your an is converging to this 1. Now, again bn is converging to 1, so let us check the rate of convergence of this bn. Again, your bn minus 1 is equal to 2 power n plus 3 divided by 2 power n plus 7 minus 1. So this is equal to 4 times 1 for 2 power n plus 7, and again we can write it as less than 4 into 1.2 power n. So therefore your bn minus 1 is less than 4 into, say this is your bn, beta n, where your beta n is 1.2 power n. Now here we can see that your bn is converging to 1 with the rate of convergence of 1 by 2n. So this implies that bn is converging to 1 with rate of convergence of order 1.2 power n. Now what is this? What do you mean by 1 by n or 1 by 2n? Now you can see that your 1/2 power n will quickly move towards the 0 in comparison to this 1 by n. So we can say that this sequence bn has the faster rate of convergence as this 1 by 2n approaches to 0 quickly in compared to this 1 by n. So in this example, I have told you that this bn has a faster rate of convergence with respect to this 1 by n. Now if you want to understand this with the help of the numerical value, just calculate it. Say this is your number of steps. Say here we have an, say here we have bn. Just put n equal to 0. For the first step, your an will be 3/7. Now let us take the help of calculator. Your an is 3/7, so this is your 0.4285. And put n equal to 0 here. Now this will be 4/8. If you put n equal to 0 here, then this will be 3 plus 1. This will be your 8. So 4/8 means 1 by 2. So this is your 0.5. Now put n equal to 1. If you put n equal to 1 in the an, then this will be your 4/8. So this is your 0.5. And your b1, put n equal to 1 here. So this will be your 5/9. So 5/9 is equal to 0.5555. So again put n equal to 2. If you put n equal to 2, then this will be your 5/9. So this is equal to 0.5555. And put n equal to 2 here. So this will be your 4 plus 3. So this is your 7 divided by, if you put n equal to 2 here, then this is your 11. So this is your 7/11. So this is 0.63636. If you put n equal to 3, then this is your, put n equal to 3, then this is your 6/10. So this is your 0.6. Now at n equal to 3, this will be your 2/3. So this is your 8 plus 3, 11 divided by 8 plus 7. So this is your 15. So this is your 0.7333. And at n equal to 4, this is your 7 upon 11, so this is your 0.6363, and if you put n equal to 4 here, then this is your 16 plus 3, 19 divided by 16 plus 7, so this is your 0.8260. Now here you can see that this sequence is converging very fast towards this one. As our sequence Bn has the convergence, as our sequence Bn is converging to 1, then you can see that from this table you can see that our sequence Bn is converging to this 1 very quickly in comparison to this An. Whereas your An is converging to this 0.6363 in fourth step, your Bn is converging to this 0.63 in the second step. So the rate of convergence of this Bn is quicker than the rate of convergence of this sequence An. So the rate of convergence is the order of this 1 by 2n in this case of Bn, and this is your order of 1 by n in the case of An. So let us define the order of convergence. Order of convergence provides the different measure of convergence speed whereas the rate of convergence examine the error values. Suppose that the error value in the nth step is xn minus, say the exact root is j. Then the rate of convergence examine individually the error values. The order of convergence examines the relationship between the successive error values, hence examine the effectiveness with which each iteration reduces the approximate error. So order of convergence provides the different measures of your convergence speed, whereas the rate of convergence examines individually the error values. Your order of convergence examines the relationship between the successive error values. Hence, examine provides you the effectiveness with which each iteration reduces the approximation error. So, let us define the mathematical definition of this order of convergence. Suppose that the sequence xn converges to x. So let xn converges to this x. Let us assume this xn converges to x, and suppose that en is the xn minus a, where a is the exact root. Then value n is greater than or equal to 0, then consider this limit n tends to infinity xn plus 1 minus x upon xn minus this x power p. Now this xn plus 1 minus x, say this is your, here our xn is converging to this x, so that means your x is equal to, so let us assume this xn minus x as en, so this will be your en plus 1 upon en power p, say this is your equal to lambda. Now here this positive number lambda is said to be asymptotic error, and this p is said to be the order of convergence of this sequence xn. Here this p is said to be order of convergence, and lambda is known as asymptotic error. This lambda is said to be asymptotic error. Now this limit en plus 1 upon en power p is equal to lambda. So we can also write it as, modulus of en plus 1 approximately equal to en power p into this lambda. Now we can also write it as less than equal to, and this modulus of en plus 1 is approximately equal to this en power p into lambda. Now for linear rate of convergence, this p will be equal to 1. Now if we suppose that we have a linear rate of convergence, if p equal to 1, that is for linear convergence, now in this case your en plus 1, modulus of en plus 1 will be approximately equal to this en lambda times modulus of en. Now modulus of en again will be less than equal to lambda times of en minus 1. Then again this will be approximately equal to lambda square en minus 2, and finally we can write en is approximately equal to lambda power n into e naught. And finally we will have modulus of en is equal to lambda power n into e naught. So here we can say that this sequence xn is converging to x with the order of convergence, with the rate of convergence of lambda power n. So for linear order of convergence, for linear convergence, this implies that your xn is converging to x with rate of convergence as order of lambda power n. So in case of order of convergence 1, your rate of convergence will be order lambda power n. So this is your rate of convergence in this linear convergence case. So the order of convergence is 1 and your rate of convergence is order lambda power n. Now let us find out the rate and order of convergence of your bisection method. So order of convergence of the bisection method. Now let us assume that the sequence xn or the root, let your xn, now we have to find out the order of convergence of the bisection method. So suppose that this xn is converging to the exact value x. So let us assume that this xn is converging to this exact value x in the interval an comma bn. So say this is your interval an, say this is your bn. Now say this is the an iteration Now in the nth iteration, as our sequence is converging to this x, now this x can be either here or at here. Now here the length of this subinterval will be equal to bn minus an. Now as our xn is converging to this x, so the length of this xn minus x will be always, if your x is lying, suppose that your x lies in this subinterval, then the length of this subinterval will be bn minus an by 2. Again, the length of the subinterval in this case will be bn minus n by 2. Now in each case, this implies that your xn minus x is always less than or equal to 1 by 2 this bn minus an in case of bisection method, because we know that in bisection method our xn will be equal to bn plus an by 2. So as our xn is equal to bn plus an by 2, now if this is the exact root, then your xn minus x will be equal to 1 by 2 bn minus an. So also this bn minus an, again this bn minus an can be written as 1 by 2 bn minus 1 into an minus 1. Suppose that our root, now say this is your bn minus 1, say this is your an minus 1, or say this is your an minus 1, this is your bn minus 1. Now the length of the subinterval will be half of bn minus 1 an minus 1. Again, just repeat this iteration. So next time we will have 1 by 2 square bn minus 2 an minus 2, then finally we will have this one equal to b power 2n minus 1 into b1 minus a1. So this bn minus an is equal to 1.2n minus 1 into b1 minus a1. Just put the value of this bn minus an here. So you can see that we have this one equal to, so therefore your xn minus x in case of bisection method is equal to 1.2n b1 minus a1. Suppose that initially let b1 equal to b and your a1 equal to a, then your modulus of xn minus x is less than or equal to 1.2 power n b minus a. Now let us assume this b minus a equal to lambda. If b minus a is equal to lambda, then your xn minus x is less than or equal to, and assume yn as 1.2 power n. So your xn minus x is less than or equal to lambda times your order of yn. Your xn minus x is equal to lambda times order of yn minus order of yn. So here we can say that your bisection method, in your bisection method, the sequence xn converges to x with the order of convergence of yn, and your yn is 1 by 2n. So this implies that in bisection method xn converges to x with rate of convergence at order of this 1.2 power n. So this is your rate of convergence. Now let us discuss the order of convergence. Now for the nth iteration we have this condition. Also for xn plus 1 minus x we will have 1.2 power n plus 1 b minus a. So this implies that xn plus 1 minus x divided by xn minus x is less than or equal to 1 by 2. So we can write this one as en plus 1. Also we can write this one as en. So your en plus 1 is approximately equal to 1 by 2 into en power 1. So here you can see that in place of p we have 1 and in place of lambda we have half. So the bisection method has the rate of convergence 1 and the asymptotic error is 1 by 2. And that is why in earlier I was talking that in case of linear convergence the rate of convergence will be order lambda power n. So here you can see that this is your order lambda power n. Your lambda is half. So this implies that lambda equal to half and p equal to 1. So the bisection method has rate of convergence, order of convergence 1 and rate of convergence order of convergence 1 and asymptotic error equal to 1 by 2. So this is the 1 by 2 is the asymptotic error, 1 is the order of convergence and order of 2 power n is the rate of convergence. Now this is all about this lecture. Now in the next lecture I will discuss the rate of convergence of the second method, rate of convergence of the Reciprocal method, rate of convergence of the iterative method for different order of iteration, and then finally we will discuss the rate of convergence of the Newton Raphson method. So thank you so much for joining this lecture.